Hello guys, welcome to another wonderful episode of CUDA Education. I'm your host, Nicholas Main. Today what I wanted to go over is synchronization in CUDA. So in a nutshell, there are two kinds of synchronization that happens in CUDA, or two basic kinds that I wanted to go over today. The first is in-block synchronization. So you have a block of threads in a kernel and you want to synchronize within that. You want to synchronize within those blocks. The second type is a device-wide synchronization, which basically means that you synchronize all blocks, all things within the kernel. So everything within that kernel that is running is synchronized and is made whole, and you could make decisions based on that. There's a subtle difference, but it's very important that you understand it when you're building your CUDA applications. One of the most important things is that the only way for you to really guarantee that all blocks within a kernel are actually synchronized and have reached a specific state is to conclude the kernel, to end the kernel, and then to start a new kernel, right? So when a kernel is running, the only real way that you could guarantee synchronization is within the block itself, right? And that has, I mean, it's a blessing in one respect, but it's also a limitation. On my graphics card, I have a 1050 Ti, GeForce GTX, what have you, 1050 Ti card. I can run 1024 threads within a block max, right? So what that means is that within my kernel, I can only guarantee synchronization of 124 threads at a time within a block, and it's the reason why CUDA has done that, or the reason why it's allowed, is that basically you give CUDA, you give the kernel, you give the programming framework the ability to run any block in any order, right? And just because a block is called block 0 or block 1 or what have you, doesn't necessarily mean that that block is going to run first. Block number 257 might run before block 0 or block 1 runs, right? So it sort of has a bit of granularity built into it, which allows you to sort of run blocks in any order, but just understand that you can't synchronize within you can't synchronize across blocks for the most part. Now there might be special circumstances in more advanced situations where you might get some synchronization, but we're not going to get into that in this video. So just to reiterate what I just said, and just for everyone to be on the same page, we're going to do a little drawing here on the Picasso wall. This is the CUDA Education Picasso wall. And by the way, my name is Nicholas Main. This is CUDA Education. Visit cudaeducation.com. You could also donate on the page. Check us out on Twitter at CUDA Education. Don't forget to subscribe to the YouTube channel and ring the bell. Yeah. So anyway, let's get into the example. So in CUDA you have what you call, let me make this thicker. In CUDA you have what you call a grid, right? And we'll just call this G. We'll just call this G. And then within the grid you have several blocks, okay? So I'm just doing this stuff real quick just so we get a bearing of what we're talking about here. Okay, so this is the block. This is a block, this is a block, and this is a block. Okay, now within the block you have various threads. Come on. Okay, and these are threads. That's a thread, that's a thread, that's a thread, that's a thread, that's a thread. Okay, so you have threads, you have the block, and then you have the grid. Now, in order for you to synchronize among these guys here, among the threads here, in order for you to synchronize among the threads, you use a term called syncthreads, and I'll show you that in the code. It's called syncthreads, and basically you basically guarantee that all these threads have reached a specific state or have done a certain amount of processing at that point in your code, right? So that's sync threads. Okay, so that's the first level of granularity. Now, as I said before, these threads here can't necessarily or really synchronize with these threads here. So these threads can reach a certain level of processing, you know, have performed certain mathematical functions, you know, gone through certain functions, certain if statements, certain loops, what have you, but you can't necessarily synchronize these threads with these threads because they're in different blocks, right? And then also in terms of communication, you could communicate, these threads can communicate with each other, but these threads can't necessarily communicate with these threads outside of very special circumstances, which is beyond the scope of this video. But you synchronize here and you can communicate here, but when you're going to different blocks, it's it's a different story. Now, so this is sync threads. Now, what device synchronization does basically is it basically takes all of this kernel or all of this grid, and it says, okay, after the grid is run or after the kernel is run, it says, okay, I want you to do a device synchronize, and what that basically means is that in the code, when you do a device synchronize, it's saying, okay, the kernel has concluded all blocks and threads and everything within the kernel has performed what it needs to perform, and then only then and there you could guarantee that the you could guarantee that that all threads in all blocks are synchronized or have reached the same conclusion or reached the same level of performance, right? So that's basically the heart of the matter. So I'm just gonna go through some code that I've created. Now, this code here is, so this code here is the warp divergence code. I've just kind of modified it a little bit to make it to show what I'm doing. Again, this is Nicholas Main. This is CUDA Education. I'm Nicholas Main. Visit cudaEducation.com. If you want to contact me for consulting, for teaching sessions, any things of that nature, just email cudaeducation@gmail.com. Okay, and you could also donate at cudaeducation.com. Okay, please subscribe to the YouTube channel. Visit CUDA Education for written instructions on maybe what I'm talking about right now. Check me out on Twitter at CUDA Education. If you have questions, the best way to do is comment on the YouTube channel. Disclaimer, this code is for teaching purposes only. CUDA Education or Nicholas Main does not guarantee the accuracy of this code in any way. This code should not be used in a production or commercial environment. Any liabilities or loss resulting from the use of this code in whole or in part will not be the responsibility of CUDA Education or Nicholas Main. All rights reserved. This code is a property of CUDA Education Nicholas Main. Please contact CUDA Education at cudaeducation@gmail.com if you'd like to use this code in any way, shape, or form. Okay, so this code is being run. I'm now running CUDA Toolkit 10, actually. I'm running CUDA Toolkit 10 right now. I'm in a Windows environment. I'm running this program here is Visual Studio 2017 Community Edition. I have an NVIDIA GeForce 1050 Ti graphics card, and my compute capability on this card is 6.5. Okay. Now, if you want to, you could install CUDA Toolkit by visiting cudaeducation.com/how-to-program CUDA. Okay, so just visit this site if you want to learn how to install the toolkit and stuff. This is for a Windows environment, but it will give you a good overview of the process regardless of your environment. Okay, so anyway, let's get into it. So what this code is doing is basically I outline the device, I select the device, I create an array of 80 million, well, you know, it's going to be a size of 80 million elements in the array. I just create a dummy variable, and then I print out the number of integers in the array. So I just print this out to the screen. Okay, and how many threads in each block will be launched in the CUDA kernel? So number of threads in each block. So I'm going to do 256 threads in each block, right? So it's 256 of these threads right here. Okay, and I just create some event variables, which you know you could investigate it more, but it's just, you know, a start and stop event, so you know when and where things are going. And then I do the dim3. So this is the block variable that basically I use it to figure out how many threads I want in my block, right? So number of threads in each block, of course, that was 256 right here. So I have 256. I have 256 threads in the block, and then I do a simple calculation to figure out how many blocks I need in order to launch launch the kernel. So you know, basically it's 80 million divided by, I guess, 256 threads. It gives you the number of blocks, or something of that nature. We're not going to get into the math too much of that, but basically down here I launch the grid. Where is it? I launch the kernel. I'm sorry, I launch the kernel, and then I synchronize and I calculate the time, and you know, I get my results printed to the screen. So this right here is the launching of the kernel, and it's just a very simple GPU function. All I'm doing is I am you know, I'm calculating the linear address of each thread, and I am saying, okay, if the thread is even, do this. If the thread is odd, do this. And that's basically it. That's not the point of the code. The point of the code is just to run something and then see how these sync threads behave. Okay, so let us just run the code and we'll see what happens. And believe me, guys, if you spend time with this, it's not too complex, but I want to just get to the point and not make my video too long, because you guys don't like long videos. So here we have the array size is 80, million. The number of blocks is this guy, over 300,000. Number of threads in each block is 256. Okay, so the elapsed time is 47.5 milliseconds, okay? So that's the elapsed time while I am syncing. I'm basically syncing all these threads all the time within each block. So remember, there are 256 threads within each block here, okay? So again, I get a time of 47.50, okay? So I'm just gonna run it again, just because, you know, these things kind of fluctuate a little bit, but let's run it again. Okay, I get 45 this time. Let's run it again. I get about 46 this time again. Let's run it again. Yeah, 46 again about. Okay. So between 47 and 46, we would say we get, okay? So now let us take out synchronization. So what are we doing? We're basically saying, okay, you don't need to synchronize all of the threads at all at the same time. So they think of these things as racehorses. You know, every time you synchronize, you're saying, okay, only after all the racehorses have passed a certain line do you get to run a different track or run in a different direction or do some other work, right? So with the sync threads, you're saying, okay, if this one goes first or goes faster, you have to wait for all the other two to finish. But we're going to take out the sync threads now. Okay, and then we're going to do rebuild. And then we're going to run the code. Okay, we still get 46. Let's see. Still get 46. Still get 46. Let me make sure that I'm not. Okay, see, we're getting a little bit faster now. We get about 45.5. So as you can see, all right, we get 46 now. But as you can see, when we take out the sync threads, we're getting slightly faster performance, right? We're dealing with very slim margins. Remember, this is milliseconds, so it's not like, you know, and it's point whatever of milliseconds. So it's not like we're re-engineering the world, you know. But as you could see, we get closer to the 46 mark, right? But let's put it back in. Let's put back in the sync threads. And just let's see what happens. So we're gonna rebuild. Actually get even faster. That's funny. Alright, let's make things a little bit more interesting. Let's make things a little bit more interesting. I'm trying to just put enough sync threads in there to really see a difference in in performance, or reliably see a difference in performance at least. Alright, now we're getting somewhere. So we're up to 47 reliably, I think. Let's see. Oh, we got to 48 now. So you see, you're sort of trying, you know, at every step you're sort of halting, right? I should have maybe put in more sync threads from the start, but you guys get the picture. See, now we're up to 48. Okay. Alright, so then now let's take out the sync threads and see what happens. Alright, so now we're back to about 46. Okay. We're going to 45 again. Alright. Okay, now let's put back in the sync threads. So we're up to 48 again. So, I mean, obviously my code is very simple and straightforward, very rudimentary, but you get the picture with the sync thread stuff, okay? So that is one thing. Now, let's keep the sync threads in. Okay. So now the next order of business is so this is just synchronizing within this, you know, within each block. So all of these are synchronizing, but remember, they're synchronizing among themselves. They're synchronizing only within the threads in the block. They don't see the other threads in the other blocks. They're only synchronizing among themselves. Okay, so the next task is that we want to see what happens when we synchronize or we don't synchronize across the kernel. So again, this is synchronizing within the threads in the block, okay? What we want to do now is synchronize we want to synchronize the entire kernel, or the entire GPU, okay? So what this would do, okay, so this guy is going to basically pause the host and pause the CPU from processing anything further until everything in the kernel has concluded. Let me say that again. CUDA ensures that all previously sent commands to the GPU has been fully processed and it has been concluded in the kernel before the host continues. So we actually have been running with cudaDeviceSynchronize in play. So what that means is that this stuff, device elapsed time, won't print until the kernel here has finished processing. And we sort of needed that because, of course, we needed to calculate the time with all these events and what have you. Okay, so the host is stopped from going forward until this is done, right? The device has concluded everything it wants. All right. Let us see what happens when we don't use CUDA device synchronize. Okay. So we're not waiting for the kernel to finish processing before the CPU reaches to this. And here we go. We have device time, elapsed time is 0.00 milliseconds. What this basically means is that the CPU, which is the host machine, this guy right here, right? We're on main, so this is all host processing, CPU processing. So it basically, what it does is it launches the kernel, and then it just continues. It doesn't stop to wait for the kernel to finish, and it just prints out what it has already. Well, what it has already is an elapsed time of 0, because the CPU is not finished processing. So whenever you want to guarantee that all blocks within your kernel or within your grid, or however you want to say it, whenever you want to guarantee that all these things have fully concluded and are completely synchronized, all threads and all blocks, the only way you can do it is to have this CUDA device synchronize here to ensure that this kernel has been concluded before you go on to further processing. So further processing, in this case, we're just printing stuff, but further processing might mean launching another kernel, right? Based on the results and everything that you get from this kernel, okay? But this guy right here is what does device-wide synchronization, or block-wide synchronization, or grid-wide synchronization, or everything to do with the kernel has finished processing before you go to the next step. So we put back in device synchronize, and of course we're back to time, okay, and it's showing time now. Another sort of alternative, you would call it, and since I have it here, and since we're it's around, I might as well just talk about it. So cudaEventRecord pretty much, for the most part, does the same thing, but it's only synchronizing up to this point. So it's saying everything before here has been concluded before we continue. So for our intents and purposes, it's basically doing the same thing, right? You still get similar times, okay? But it's just an event-based synchronization. So maybe it is you want to just make sure that maybe you have two kernels. You have a kernel here, and then you have a kernel here. Maybe it is that you just want to guarantee that this kernel is finished before you continue on to more processing. So if you just care about this kernel, you would do a cudaEventRecord and then stop, and then this barrier would just proceed as long as this has finished, and you could continue. With CUDA device synchronize, everything before here has to be concluded. There's no sort of granularity or any kind of detail that you could say, okay, you know, I want you to ensure that this is done, but not this kernel here. No, with cudaDeviceSynchronize, everything before it dealing with the GPU has to be concluded before it goes forward. So you could use cudaEventRecord to sort of have a little bit more control or granularity over your code. While we're here, let us do a quick experiment, and I hope I don't crash and embarrass myself, but it's okay. Let's do a little experiment. So since we're doing cudaEventRecord and we're stopping here, it shouldn't care about this guy right here, and it should give us a similar reading for the time. Okay, right, so we get a similar reading for the time. It doesn't care. I'll just rebuild one more time just to make sure you guys believe me. Okay. Alright, so we sort of get similar time. It doesn't care about this kernel here. Okay? But let's do a little trick. We're gonna move this event thing and we're gonna say, okay, I'm gonna care about both kernels. Right? So now I'm saying, okay, run this, and we're only going to pass this barrier, this line of code, once both of these are finished. Now, with my way of thinking, what should happen is that we should get something higher than what we got before, because of course we're doing two kernels. Ooh, look at that. We get 95.411. See? And you could sort of understand why that happens, because now we're waiting for these two kernels to finish. Now let's really go crazy with this. So we're gonna rebuild. Alright, so now we're up into the triple digits. Okay, so as you can see, you know, it balloons. Now of course I could still just go back to doing one of them, and you see now we're back down to 44. Okay, so this CUDA EventRecord gives you a little bit more granularity or control over what and where you want to put the barrier in your code, and what you care about and what you don't care about. Now, having said that, let us do cudaDeviceSynchronize. Now, also cudaDeviceSynchronize, as far as I can tell, it doesn't take any arguments. You can't put anything in cudaDeviceSynchronize. It will, I think it will just say that it doesn't expect an argument or something. We could test it out, but let us see what happens now. Okay, we get 48.9506. That doesn't make sense, because it's supposed to wait for all of them. Hold on. Oh, it's still showing. Hold on. Oh, I I know what happened. I know what happened. The reason is because let me think this through. Okay, it's still telling me 47, but the reason is because of how I'm calculating the time. So let's say I got rid of this guy and I said only record the time after device synchronize has finished, right? So my stop now is basically looking for this guy. Okay, so obviously the barrier here has to pass before, so we should I have to rebuild. Come on, rebuild. Now I'm not getting anything. Why is that? Why am I not getting anything? Alright guys, I finally figured out what's going on. So apparently this cudaEventRecord it actually doesn't care about the CUDA event synchronization. So what happens is that let's say I take out this CUDA event synchronize, right? It's going to actually record this as being reached, even though this has been, even though CUDA device synchronize has been issued. So even though it's been issued, this guy, the event is still recorded as being stopped, right? So that is why when I do just CUDA device synchronize, it just records as 00 as in further processing has been done, or no processing has been halted. But actually this actually hasn't really been proceeded until all of these things are done. So what I'm going to do to test the theory and you know, see if this is actually working, is I am going to overload this stuff with a bunch of things. Okay, so I just want to see how long the command prompt takes before. Let me just close all these guys. Okay, so it's taking some time. So you see, it won't print out anything. It won't reach down here until the CUDA device synchronize is done. But this CUDA event record, it still says, okay, well, the CPU has read all this stuff, it's read this, and then it's read here. So you know, it that's the only thing that maybe passes through the barrier. Let me try. So that's why I get a reading of 0 for the time. But let's try to see if I could get it to damn it, man. Let me see if I could force it to actually wait. So this assignment would represent further processing, right? So I'm hoping that this processing right here will prevent the CPU from going any further and recording this thing as a stop event. Okay, so let's see if that works. Man, I did not expect this CUDA event thing to be so crazy. Okay. Alright, so we're back on the grind. No, it still shows 0. Yeah, this is one for the ages. I guess you have to do a CUDA event synchronize. See, it will show the time now. Oh, actually, no. Have to do cudaEventRecord. Yeah, we'll show the time now, but okay. So this CUDA event stuff is a little bit it's a task on its own. So I am forced to actually synchronize on the event, even though I do run this CUDA device synchronize. Yeah. Okay, but basically this CUDA device synchronize, it, you know, regardless if I take out all the CUDA event synchronize and all that stuff, it will still wait for all of these kernels to finish launching and concluding before it proceeds, right? You sort of have to manage the event stuff by itself, right? So, you know, it takes some time. So let's say I double this. Okay, all right. So at least we know that this is still working. Now, you know, our actual recording of the metric, you know, that gets a little bit more involved. I guess we'll get some time here. Yeah, I still have to synchronize on the event. I can't get a good reading unless I synchronize on the event. I was just hoping that this processing wouldn't be done until this synchronization happened, but that is not the case. So again, let us just play with the granularity a little bit. So let's say I take this event thing and I say I only care about this guy, right? So it prints out everything, but it's still the GPU is still busy. So that's I guess the icing on the cake. So we'll do that again. So it prints out. I'll do it again. Sorry. So come on. Let's do it again. So it prints out everything immediately, but then it's going to wait for everything else on the GPU to finish processing, and then it gives me the press any key to continue. So let me get a little bit more granularity on it. So let's not do here, but let's do down here. Maybe here. Okay. So there you go, folks. You get an idea of how all of this works. Just be careful that whenever you're using an event stuff, to make sure you synchronize on the event, because if you don't, regardless of whatever you do above, it's going to record the time disregarding this device synchronize thing. Because I guess what's happening, this only really relates to the device, and this CUDA event stuff is really a host function, so it's not going to really heed to this device synchronization. The device synchronization only cares about the GPU, right? And CUDA event, I guess, is a host defined stuff, host defined function, so it disregards that completely. Let me get my, so I will clean up this code. Where is my, come on, right. So I'll clean up this code and make it available on cudaEducation.com. Guys, make sure to donate. I'm pretty much the only person doing this kind of stuff, so it takes a lot of my time and energy to do it. And resources, so help those that help you. Now you understand what syncthreads does, you understand CUDA event synchronize, you understand CUDA event start and stop, you understand CUDA device synchronize, right? Yeah. Now, I'm not going to say that necessarily that you can replace this guy with this guy. I'm not going to go that far. That's, you know, that's making a huge assumption. So always, if you want to make sure that your device is finished concluding all its business, make sure you use the CUDA device synchronize. Don't just assume that, okay, I can synchronize on the event, and that event means everything else preceding has been done, therefore I don't need this guy. I would not make that leap of faith, okay? You really have to do testing to really see the behavior, see if what the behavior is what's expected, just like what happened with me. You know, for me to say that, okay, you could just synchronize on the event and not synchronize on the device, that would be reckless, because I'm not sure if this has more, you know, more overarching things that it's doing that the CUDA event synchronize is not doing, right? So again, I'll read the disclaimer. This code is for teaching purposes only. CUDA Education and Nicholas Main does not guarantee the accuracy of this code in any way. This code should not be used in a production or commercial environment. Any liabilities or loss resulting from the use of this code in whole or in part will not be the responsibility of CUDA Education or Nicholas Main. Okay? So you guys understand what's going on. Alright, thank you for watching. You've gotten almost an hour of my time, so that's more than enough. But you guys now understand how this thing all works, and you could definitely run it yourself and see. I will post it on cudaEducation.com. I'll put the link below. Alright, you guys have a great day.